Yeah, thanks to Rutger and Sangil and all the organisers. Hopefully everyone's recovered from the banquet last night. So yeah, I'm going to be talking about Transversal Matroids. So the reason to talk about Transversal Matroids, in my opinion, is if you look at the chapter 1 of Oxley, which is like the premier textbook on Matroid theory, there's these 3 types of Matroids in chapter 1. We've already heard about representable Matroids a bit, and we've heard about types of graphic Matroids, like gain graphic Matroids and such, but we haven't heard about transversal Matroids. So I'm going to talk about those. What are transversal Matroids? Well, they have this sort of not too complicated definition. So you just have a bipartite graph, and you pick one side of the bipartite graph, which for us is going to be the bottom set of vertices, and that's going to be the ground set of your Matroid. And then a set is independent if and only if it can be matched into the top. So this set here, this set here is independent, and this is actually a basis because I can't match anything else. I've already saturated the top. So they have this sort of rather straightforward, innocent-looking definition, but there's actually some sort of evil hiding under the surface here. So if we compare them to our other types of Matroids, we can look at representable Matroids first. And representable Matroids are basically perfect. They have everything you want. They're closed under duality, they're closed under minors, and not only that, but if I have a matrix representation of a Matroid, and I want to find a minor or a dual, then I can do that very easily in polynomial time with matrix operations. So they're basically everything we would want from a class of Matroids. Graphic Matroids aren't quite as good, but they almost are. So they're closed under minors, obviously, because they're sort of where we get minors from in the first place. And it's very easy to find minors of graphic Matroids as well. And they're not all closed under duality, but if you want to figure out if a specific graphic Matroid is co-graphic, then you just have to ask, is the graph planar? And if it is, we can find the planar dual very easily, and that will be a representation of the dual. So they're not closed under duality, but they're basically as good as you could hope for without being closed under duality. Transversal Matroids, on the other hand, have none of these properties. So they're not closed under minors, they're not closed under duality, and it's actually really hard to tell. So if I have a minor or a dual of a transversal Matroid, is it transversal? If it is transversal, what does it look like? So this problem is actually not even in NP. It's harder than that if you know anything about complexity theory. So this is really hard. Transversal Matroids are just really bad at everything. So we sort of get these nice natural questions which have been asked a long time ago. So in 1971, Dominic Welsh asked if we could characterize the class of Matroids that are both transversal and co-transversal. So that's sort of asking for the duality problem. Obviously, it's very easy to classify this. It's very easy to characterize this class of Matroids. It's characterized right here. But what he's actually asking is if we can find a polynomial time algorithm to characterize these things. So we want an algorithm that will determine whether a transversal Matroid is co-transversal or not. And of course, we can ask the same question for minors. But I should specify that transversal Matroids actually are closed under deletion. If I want to delete an element, I can just delete the vertex from the graph. It's the same as deleting the element. So they are closed under deletion. So what we really care about is this problem, but only for contractions. So these problems have been around for 50 years. So obviously there must have been lots of work done on them. So I've compiled this nice list of all the stuff that's been done on them up until now. So unfortunately it's a bit sparse, but you know, there's some encouraging things about this, because if this means if we can prove absolutely anything at all, that will be a new result. So, you know, that's kind of okay. So what we're going to do is we want to look at contractions of a transversal Matroid. We're going to look at the duality problem as well, but we'll look at contractions first. So basically we want to find a polynomial time algorithm that can determine if a contraction of a transversal Matroid is transversal, and if it is, what does the transversal representation look like? Is the problem we're sort of going for. But contraction, at least to me, is kind of unintuitive. It's a bit confusing. We'd much rather do deletion. So let's do that instead. So we're going to look at the duals of transversal Matroids. So they have the duals of transversal Matroids have this nice characterization as well. Not transversal Matroids, of course, because they're not closed under duality. but they have a different representation. So what we do is we take a directed graph, and the vertices of our directed graph are going to be the ground set of the Matroid, and then we pick a special set of vertices to be the terminals, which is the set S, and then a set of vertices is independent if for each vertex in that set we can find a directed path to the terminals such that all of our paths are disjoint. So this set of red vertices here is independent because this vertex here is already in the terminal set, so I can just have the path that consists only of itself. And then this vertex here, it can't go along here because that would intersect with my other path, but it can go down here. And then this last vertex can go this way. So for example, these three vertices at the back would not be independent because any path from this vertex is going to intersect with one of the other paths. So yeah, we get this nice a new type of Matroid, which is called a strict gamoid, if it can be represented in this way. And it turns out that these Matroids are exactly the class of duals of transversal Matroids. So what does that look like? Well, what I'm going to do is I'm going to take a transversal Matroid and a basis, and then match the basis, find some matching of the basis. And then I'm going to turn this into the dual as a strict gamoid. So what I do is I direct all the edges down. That's fairly straightforward. And then I'm going to I'm going to contract each of my matched edges. So what's that going to look like? Well, I'll contract this one here first. So that goes up there. Then I'm going to contract this edge here. That goes up there. And then so on. That one goes up there. And that one goes up there. And now I need a set of terminals. I'm just going to make these ones the terminals that I haven't used yet. And it turns out that this particular strict gamoid is actually the one we had before. So this vertex here sees these three terminals. This vertex sees one terminal and that one. And so this one is the same thing. And this one sees those two. So this is actually this graph we had before. And it turns out this is the dual of the other Matroid. It's not straightforward to see why that is, but that is the case. And you can reverse this process as well. So these are exactly the duals of transversal Matroids. So we can now turn our problem into a new problem of we want to find a polynomial time algorithm that determines whether a minor of a strict gamoid is a strict gamoid. Now, because transversal Matroids are closed into deletion, that means strict gamoids are closed into contraction, and there's a very easy way to look at that. So all we need to actually do is figure out so we're only caring about deletion now, so we want restrictions. Now, if I want to delete an element from my strict gamoid, it's actually, I can't just delete the vertex. Because, for example, in this strict gamoid here, these two vertices are independent, but if I delete this vertex over here, then they would be dependent. So I can't just delete vertices and still have the same Matroid that I want. But what I can do is I can just say, okay, this vertex here that I'm trying to delete is now just not in my Matroid anymore. So the ground set is a subset of the vertex set. And I have some other vertices which I've deleted, but they're still there. And if I do that, I get what's called a gamoid. So basically, our problem is we're looking at a gamoid, and we want to find out, okay, is there a representation of this gamoid that is a strict gamoid, that has none of these sphere vertices floating around? So yes, this is our problem for the minor's problem. Now, it turns out that this problem actually also solves the duality problem if we can solve it in general. So the reason for that is if I have a transversal Matroid, I can turn it into a gamoid incredibly easily. All I do is direct all the edges up, and then all these vertices at the top, they of course aren't in my Matroid. Remember, my Matroid is these vertices down here. So these vertices are going to get my special empty vertex treatment. And I'm going to put all of those vertices into my terminal set. So now I have a gamoid. And it's pretty easy to see that any matching of this Matroid corresponds directly to a linking of this Matroid and vice versa. So they're pretty clearly the same Matroid. So every transversal Matroid is actually a gamoid. And what we're trying to do, well, one of the things we're trying to do is work out, is a transversal Matroid is its dual transversal? And because the duals of transversal Matroids are strict gamoids, if a transversal Matroid is also a strict gamoid, then its dual will be transversal. So the equivalent question is basically figuring out, okay, is this transversal Matroid also a strict gamoid? And we can do that by looking at this gamoid, and if we can figure out a way to delete all these vertices and ask, is this new Matroid a strict gamoid, then we'll have solved that problem. We'll be able to figure out if this Matroid is a strict gamoid, which means this one's a strict gamoid, which means its dual is transversal, and we'll have solved the duality problem. So yeah, if this turns out that if we can solve this restriction problem for strict gamoids, we can solve the duality problem for transversal matroids. So they're all sort of one problem. Unfortunately, we couldn't, as you may have been able to tell from the title of this talk, we couldn't solve that problem, but we could solve deleting one element of a strict gamoid. So the way we're going to do that is we're going to ask, okay, we have a, if I go back a bit, we have a strict gamoid that we start with, we delete one element, one vertex, and we ask, is this new matroid a strict gamoid? And how do we tell if the matroid is a strict gamoid? So, yeah, this is our problem. So we're going to have a single element restriction just for now. Hopefully we'll be able to extend to more elements in the future, but for now we just got a single element. And our matroid is going to be M plus will be the strict gamoid with the element in it, and then M is going to be the matroid without the element. So we've deleted this one element. And we want to figure out if M is a strict gamoid. And ideally we want to do it in polynomial time. So what we need is a way to tell if a matroid is a strict gamoid. And to do that, we're going to use our old friends from previous talks, cyclic flats. So yeah, here's a definition in case we've forgotten what they are. So a cyclic flats is a flat that happens to be a union of circuits. And we're going to denote the collection of cyclic flats as this curly Z of M. And we can use cyclic flats to tell us certain things about matroids. They're actually very useful for transversal matroids and strict gamoids. So going back to transversal matroids for a bit, there's this formula from the 70s that says exactly when a matroid is transversal. So what we do is we calculate this beta value on every set in X. So we start by doing that, so it's sort of a recursive formula, so we start at the top. So we calculate beta for the whole ground set, which is going to be 0, and then we move down. And when we get to a certain set X, the beta value of that set is going to be the rank of the matroid minus the rank of the set minus the sums of all the beta values of cyclic flats that contain that set. So we're sort of working our way down. We care about all the cyclic flats that contain the set we're looking at, and then we can calculate this formula for beta. And it turns out that if beta is non-negative for every set in the matroid, then it's a transversal matroid, and that's the only, so it's the if and only if characterization. So it's a very nice characterization. Unfortunately, it's calculating something for every set in the matroid is not polynomial time. And even if you had a certificate that said your matroid was not transversal, i.e. you had a set where the beta value was negative, the formula that verifies that could involve exponentially many cyclic flats. So this is not a good way, if we're dealing with polynomial time, to figure out if something's a transversal or not. But we're still going to use it to help us out. So we can, but remember, we're working in the strict gamoid world, so we can dualize all of this. So there's a few calculations you can do to show that this version of the formula is the same formula but for strict gamoids. So we replace beta with gamma because we're working with gamoids and it sounds like gamma. And we sort of do some calculations and it turns out this is the formula. So I like this one more because it's building up from the bottom. So you start with the empty set which has a gamma value of 0 and then you work your way up. So the gamma value of a set is going to be the size minus its rank, which is the nullity of the set. And then you also subtract off the sums of all the gamma values of cyclic flats that are contained within the set. So you're sort of building upwards rather than down, which to me feels a bit more intuitive. So we get this dual result, and then again, this tells us exactly when something is a strict gamoid. It's only if everything's positive, non-negative. So yeah, we get this nice result there, which we're going to use, but of course, it's not polynomial time by itself. And I think, oh yeah, so what we want to do is be able to read the gamma values that we need right off the graph. And it turns out there's a nice easy way to do that. So if we do if we take a representation and we maximize it, so that just means we add in all the edges that we can, all the directed edges that we can, without changing the matroid at all. Then what happens is each, we can look at what's called closed forward neighborhoods. So the forward neighborhood of a vertex C is going to be the set of vertices with a directed edge into them from C. So F and E is the forward neighborhood of C. And the closed forward neighborhood is just that set plus C itself. So C, E, F is a closed forward neighborhood in this graph. And it turns out that the closed forward neighborhoods correspond directly to cyclic flats with non-zero gamma values. So this C, E, F here is a closed forward neighborhood, and it's going to have a gamma value of 1. Whereas if I look at this other set over here, A, B, C, D, that's a closed forward neighborhood as well. It's a closed forward neighborhood of A, but it's also a closed forward neighborhood of B. And because there's 2 vertices with that closed forward neighborhood, it has gamma value of 2. So you can basically just read all the gamma values directly off the graph. It's very convenient. Every other cyclic flat that's not a neighborhood is going to have a gamma value of 0. And yeah, we don't know the non-cyclic flat gamma values, but those aren't super important. We can get those later. So it turns out that we can read this off, and then what we're going to do is we're going to use these results that we've got from this graph to figure out what happens, because remember we're deleting an element. So m plus is our strict gamoid. We can just read the gamma values off that, and then we want to figure out what happens to the gamma values in m based on that. And there's a bunch of formulas that I'm not going to go over, which tells you what happens, and you can figure stuff out. But it turns out that if I just skip all the actual results, we get this algorithm. So we say the set of cyclic flats that have non-zero gamma value is going to be the set F from m plus, and remember m is the matroid after we deleted the element. So first we check the gamma values of all of those cyclic flats in F after we deleted E. That's pretty easy to check. And then we can check all of their joins. Remember, cyclic flats form a lattice. We've seen that before. And then we have to check the joins of those joins as well, which is a bit slow. It does take a while, but it's still polynomial time. And it turns out if we check all 3 of these sets, then if there is a negative gamma value of a cyclic flat in M, it has to appear somewhere in here. There has to be at least one in here as well. So we'll find if it has a negative gamma value of a cyclic flat. And if we don't find that, then that means that all the other cyclic flats that we didn't check have to have gamma values of 0. So then we can construct our matroid as well. And there's one more step, which is, this is all just for cyclic flats. We have to check every other set as well, because remember, these formulas apply for every set in the matroid, not just for cyclic flats. We just use the cyclic flats to calculate the gamma values. So then we do some other tricks, which I'm not going to specify, to check everything else. And then we can verify that our matroid is a strict gamoid or not in polynomial time. And we get these results. So yeah, this is just for one element, unfortunately. However, so yeah, we get this result, and we can, of course, get the dual, which is the corollary in transversal matroids. However, some of these results that we used here, which I didn't put up, but some of the results we used for this algorithm do actually apply, not for the general case of any deletion, but they do apply specifically when I'm deleting what's called a fundamental basis, which is exactly this set here. I'm sort of not hopeful that we can find an algorithm that works for any set in the strict gamoid, but I am hopeful that we can find an algorithm that works for a fundamental basis, which is exactly what we need to do this duality problem. So there's a hope that we can find a polynomial time algorithm that solves this 50-year-old conjecture. And yeah, that's the result, and that's the hope, and that's the talk.
Thank you, Sam. Are there any questions? We've got time for at least one quick question.
Is the picture just hopeless for excluded minors?
For gamoids?
Well, I guess when the question is to characterize these things, you said it means an algorithm, but you could also say it means an excluded minor characterization. So what happens when you ask that question?
Well, transversal matroids aren't closed under minors, but if you close them under minors, you get gamoids.
Oh, right, yeah.
And yeah, this is sort of the problem is they don't have any nice, but you can get gamoids. Gamoids are closed under minors, and they are the closure of transversal matroids under minors. But they have infinitely many excluded minors, and not only that, but I think there's a result which says every gamoid, you can find an excluded minor for the class of gamoids that contains that gamoid as a minor. So it's basically hopeless for finding excluded minors for gamoids. So yeah, excluded minors aren't really the way to go for us.
Okay.
Yeah, that result's an amazing result, but Dylan only put it in the Matroid Union blog. Oh, is it? Oh.
If the answer is yes, can you find the representation as well, the algorithm?
Oh, yes, you can. So I should have mentioned that. So this algorithm, so what happens is we find the cyclic flats that have, we check all these cyclic flats, and it turns out that the ones that we checked, if there are no negative ones, they will be all the ones that aren't 0. And once we have all of those, we can just construct these closed forward neighborhoods directly from them using this result here. So then we can directly construct the representation. So yeah.
Okay, well, I think we're running a bit short of time, so we'll thank